Okay, so welcome to this video lecture. This one is on section 4.5, where we're going to start talking about the graphs of logarithmic functions, so what those graphs look like. So 4.5, graphs of logarithmic functions. Okay, so to do this, I want to use a particular example, and I want to use the fact that we know that the exponential functions and log functions are inverses of one another, okay? So what I'm going to do is I'm going to make a table of values for a particular exponential function, and the one I want to use in my example is just 2 to the x. Okay, so here's my table. Actually, I'll just do a horizontal table. Let's say this is x, this is f of x, which in this case is going to be 2 to the x. Let me pick a bunch of values. So let's use -3, -2, -1, 0, 1, 2, 3. And then I'm going to plug them in, right? So if I plug in -3, well, what's 2 to the -3? That's going to be 1 over 2 cubed, right? So that'll be 1/8. If I plug in -2, then I have 2 to the -2. But that's the same as, do you guys see where this came from? So this is 2 to -3, which is 1 over 2 to the third, but that's just 1/8. So if I do 2 to -2, this is going to be 1/4. 2 to the -1 is 1/2. Anything to the 0 power is 1, so 2 to the 0 is going to be 1. Then 2 to the 1 power will be 2. Right? 2 to the second power, 2 squared is 2 times 2, that's 4. And then 2 to the third power, 2 times 2 times 2, that's going to be 8. Okay, now let's look at the log function. And the particular log function we want is log base 2. So the function f of x equals log base 2 of x is the inverse of the function above, right? So it's the inverse of f of x equals 2 to the x, right? If I take the composition of those two, I'm going to get x back. So that means the table of values must be the following. So if I make a little table here, so now this is x, this is f of x, but now this is log base 2 of x. Okay, and I'm going to have the same. Okay, so because these are inverse functions, right? Remember from up above, let me go back to this table. If I had, if my input to the 2 to the x function was -3, the output was 1/8. If the input was -2, the output was 1/4, and so on. But since this log base 2 of x is the inverse of it, those values flip, right? So now what I'm saying is if the input to the log is 1/8, what's the output? It must be -3, right? If the input to the log function is 1/4, then the output must be -2. Right? That's what it means to be an inverse function. So if this is 1/2, this is -1. If this is 1, then the log of 1 is going to be 0. If this is 2, the log base 2 of 2 is 1, right, which we know. If this is 4, this is going to be 2. And if this is 8, this is going to be 3. Okay. Do you guys see that, right? Because they're inverse functions, the input and outputs are going to exchange roles, basically. That's another way of saying it. All right, so let's see what this looks like. Let me plot this. Here, I'll do it in Desmos, and then we can talk about it. Okay, so here's the graph, right, of the function. Notice several things about this graph. So the first thing is that there is a vertical asymptote. And it's basically the y-axis, right? So it has the equation, the vertical line is x is equal to 0. Because as the input gets closer and closer and closer to the 0 from the right? So as we go in this direction, as we get closer and closer and closer to 0, what happens to the function? It's going down towards -infinity, right? It never quite reaches, never touches 0, but it's going down towards -infinity as x gets closer and closer and closer to 0. So there's a vertical asymptote at x equals 0. That's one thing. And notice that the log function can never be negative, right? You don't see it over here. So you can't take the log of a negative number. It's undefined. Okay, another thing to notice. The horizontal intercept. So this point right here. This is going to be the point 1, 0, right? So what it's saying is that the log base 2 of 1 is equal to 0, right? So it's saying the log, and this is going to be true for any base 2 of 1 is equal to 0. Why is that? Remember, if you write this as an exponential, you would say 2 to the 0 is equal to 1. And any base, b to the 0, is always equal to 1, right? It doesn't matter what the base is. So the log functions will always pass through 1, 0. What else do we know? Well, it's increasing, right? So I'll write the function is increasing because it's getting larger and larger and larger. And it's concave down. Okay, so it's increasing, concave down. The domain is 0 to infinity, but not including 0, right? Because it can't actually equal, the input can't actually be 0, just a little bit more than 0, all the way to infinity. But the range actually varies from -infinity to +infinity. So the outputs, right, the y value can go from -infinity to +infinity. So eventually it will reach infinity as you keep going to the right. And so I've said this before, let me write it out though. So as x approaches 0 from the right, then the function is going towards -infinity. And that's what we mean by this, right? As the input gets closer and closer to 0, this function goes down towards -infinity. So that's why we have a vertical asymptote at x equals 0. And if we go the other way, so as x approaches infinity, so now as this input gets larger and larger and larger, the function's growing, and it's going towards infinity, but it's doing so very, very slowly. right? So you may have heard like logs grow slowly, and that's what they mean by this. So the function is going towards infinity, but very slowly. Okay. Another thing, remember that when you plot a function and its inverse, they're going to be reflections about the line y equals x. So if I plot 2 to the x and I plot this function log base 2 of x, they should be reflections, right, about the line y is equal to x. Let's actually look at that. Let me show you that. I'll make another graph. Okay, so we can see that here. So remember, this was, this was our log function, f of x equals log base 2 of x. This was our exponential function in red. So this is 2 to the x. And then this is just the line y equals x. So they're reflections of one another, right? They're inverse functions, so they're going to be reflections about the line y equals x. The other thing to notice is that, remember the domain and range are going to flip values. So we just said for the log function, the domain was 0, but not including 0, comma, infinity, right? Those are all the possible input values, all the possible x's, but they can't be negative. So from 0, but not including 0, all the way to infinity. And then the range was all the possible output values, and that was the entire, all the real numbers, right? So from negative infinity to positive infinity. So the y could be from negative infinity all the way to positive infinity. Now, because 2 to the x is an inverse of the log function or vice versa, then the domain and range for the exponential function 2 to the x are going to flip, right? So in this case, the domain would be the range of the log function, right? The domain of the exponential would be the range of the log. So this domain would be from negative infinity to infinity. And we can see that here, right? Because remember, the exponential can be negative or positive. It goes from negative infinity all the way to positive infinity. And then the range is going to be the domain of the log. So it goes from 0 to positive infinity. Okay, and again, we can see that because the exponential approaches 0 but never quite reaches 0, right? So it goes from 0 but not including 0, and then it can go all the way up. The output can always be up all the way up to positive infinity. It can grow without bound. Right? And again, that's because those two functions are inverses of one another. Okay, it turns out that the larger the base in the log functions, the slower that the graph grows. So let me show you that. Okay, so again, the larger, I'll go back to draw. The larger the base, the slower that the logarithmic graph grows. And if you plug in numbers, you'll see that makes sense. But we can also see it from this picture here. So again, I just did these graphs on Desmos. So the blue one, actually, let me start with the purple. The purple is log base 2. So this is f of x equals log base 2 of x. Then I increase the base a little bit. In fact, the next one is natural log of x. But remember, that means log base e of x. And e is larger than 2, right? It's like 2.7 something. And then the third one is, this is just the log of x. But remember, if I don't write any base, this means log base 10 of x. So the base is getting larger, and what's happening? Well, if you look here, the graph is growing more slowly, right? So here, the purple one is log base 2 of x. Then the green is log base e, so it's growing more slowly. And then 10 is even more slowly. If you kept going, you find it's even more slowly, right? They will all get to infinity, but they grow very, very slowly. It takes a long time to get to infinity. Okay. Actually, let's do a question about the domain. Let's say I want to find the domain of this log function. F of x equals, say, natural log of 7 minus 3x. Okay, so remember domain. What are all the inputs, all the x's that are okay? Well, I have an issue here. I have to be careful here, right? Remember, for logs, the argument cannot be negative. It has to be greater than 0. In fact, it can't even be 0, right? It's undefined if it's 0 or negative. So the argument, in this case, the 7 minus 3x, would have to be greater than 0, right? In order for that to give me a real number output. Okay, great. So I'll just set it greater than 0, and then I'll solve for x. So how do I solve this for x? Well, I would subtract 7 from both sides. So I have negative 3x is greater than, and then 0 minus 7 is negative 7. Then I would have to divide both sides by negative 3. But remember, this is like that one special rule. If I divide by a negative value or multiply by a negative, typically it's division at the end, like I'm doing now, then what do I need to do with that inequality? I need to flip it, or I need to change the sense of the inequality. So now it becomes less than, and then negative 7 divided by negative 3 is positive 7/3. So that would be all the possible x values that would make that a real number, right? That would be okay for the domain. So the domain would actually be, if I write it in interval notation, domain will be any number from negative infinity to 7/3, but not including 7/3. Okay, now let's talk about transformation of log functions, of these graphs, of these log graphs, where we can shift them or expand them, that sort of thing. So transformation of log functions. Okay, so one thing that's sort of interesting, if we look at the change of base formula, remember what it says is that log base b of x is equal to log base c of x over log base c of b. But I can write this as 1 over log base c of b times log base c of x. So really what I'm saying is that, right, since this is now this log base c of x is being multiplied by this term, I can think of this as So log base b of x is really a vertical expansion or compression of log base c of x. So it was a vertical expansion, which is like a stretching, right? Actually, let me just use stretch. Vertical stretch. So stretching or compressing of log base c of x. Okay, so if you change the base, it's really a vertical stretch or compression of the original log. And then the other case is a horizontal compression or stretching and compressing or expansion or stretching. In that case, so a horizontal stretching or compressing also compression. So remember what that means, right? If we write this as, if I have log of x, but then I multiply the x by some value, say c in this case, or I think we used k when we talked about this in chapter 1. What does that do? Remember, if I multiply the input, the x, by a particular value, it's going to stretch it or compress it horizontally. And it's by the factor 1 over c, right? But in this case with logs, we can write this a little bit differently, right? This is really the same. So say this horizontal stretching or compressing, when I multiply the x by a value, this is the same as a vertical shift, and you'll see why in a second. So is the same as a vertical shift. Right, a shift either up or down. Why? Because remember, log of a product is the sum of the log. So this is log base c plus log of x. So really what you're saying, I'll just reverse those, right? I'm saying that log of c times x, which is what we know as a horizontal stretching or compression, right? When I multiply the x by some value. Well, that's the same as the original function, log of x, plus some new value, log of c. And remember, when I add something to a function, when am I doing it? I'm shifting it vertically. So it turns out a compression or a stretching horizontally is the same as shifting the entire original log function vertically, either up or down. All right, so let's do some graphs to actually show this. So in this case, what I want to do, and again, I'll do the actual graph on Desmos and copy it in. I want to sketch a graph of f of x equals natural log of x, so that'll be my regular one, and then another graph, say g of x, which is equal to natural log of x plus 3. Okay, so let me do that next. Okay, so if we look at this black graph, was the original function, so this is f of x equals natural log of x. And then the red graph is the second one. So this was natural log of x plus 3. Okay, and it looks like it is the same exact graph, natural log of x, but it's shifted vertically up by 3 units. Do you guys see that? So it's shifted vertically up by 3 units. But there's another way you can think about this. So I could also write so remember g of x was the shifting up by 3, right? So this is natural log of x plus 3. So another way of writing g of x can also be written as natural log of x, and then I'm going to write 3 plus 3 in a funny way. I'm going to write it as natural log of e to the 3rd power. And remember, that's just 3, right? Because the natural log undoes the exponential, e to the 3, and it gives you back the argument, which is 3, right? So this is true because natural log of e to the 3 is just 3, right? It's just a different way of writing 3. But when it's written this way, I can use my property of logs. Remember, if I have a sum, I can write that as the log of the product of the two things. E to the 3 is just some number, right? Whatever it is. We can do this out. Actually, let me do that. It turns out that e to the 3 is around 20.1. So what this is saying, right? Remember, if I multiply my x by a particular value, it's going to be a horizontal either stretching or compression. And since this value is larger than 1, it's a compression. And it's compression by the factor 1 over 20.1. Right? Remember, it's always the inverse. It's a reciprocal. So it's a compression by 1 over 20.1. So what I'm saying is, if you look at this picture, you can either think of it as a shift up by 3, right? So you start with the original natural log of x. So this one right here. And then if I add 3, it's either a shift up by 3, or if I write it in this different way, right? If I write it as natural log of e to the 3 times x, which is natural log of 20.1 times x, then you can also think of this equivalently as taking this original function and compressing it by a factor of 1 over 20.1. Right? So if you compress this horizontally, you're going to get the same red curve. Okay, so really those two transformations are equivalent. All right, so what I want to do now is talk about transformations of logs in general. And then using that information, I'm going to give you guys a bunch of graphs, or we're going to work through a bunch of problems where we're given graphs, and we're going to have to come up with the function, with the log function, just given the graph. Okay? So let's talk a little bit about that. Let me do a new page here. So transformations, of logarithms. All right, so here is like the key thing. Any transformed logarithmic function can be written in the form f of x equals a times log, and I'm just going to use base 10 here, x minus b plus k. Or, and here's where you have to be careful, so or you might have to write it this way as a times log of negative what's inside x minus b plus k. When would you have to use that second form? If the graph is horizontally reflected, if it's reflected about a vertical axis. So I'll say if horizontally reflected. Right? If it's not, and you'll know that immediately by looking at the graph, whether it's flipped about a vertical axis or not. If it's not, then you use the first one. If it is flipped, then we have to use that second one, where we have to put that negative in. Remember, the negative of the argument flips it about a vertical axis. Okay, and what else do we know? The b here turns out to be the vertical asymptote. So where the line x equals b is the vertical asymptote. Okay, so I'm going to give you a graph, and we want to find the formula for that log function. All right, so let me pause this and okay, so here is the graph, and I want to find a formula for the function of that graph. It's a log, right? It's some sort of transformed log function. So if we look at this, first thing, right? Where is the vertical asymptote? Well, if you look at this, right, this graph is going down towards negative infinity as x is approaching 1. So it looks like x equals 1, that vertical line there, is my vertical asymptote, right? So let's write that down first. So I know I have a vertical asymptote and it has the formula x equals 1. What does that tell me? Well, it tells me that my b is equal to 1, right? So therefore I'll say b we know is equal to 1, right? Because remember, the b is going to be the vertical asymptote. What else do I know? So the question is, does this look like a regular log function that, remember, it would go up and go in that direction towards the right and go towards positive infinity as x gets larger? Or does it look like it's flipped, reflected about a vertical axis? Well, in this case, it looks like it's flipped, right? Because it's reflected about that line y equals 1. So what form do we use? Remember, we had those two possibilities. Well, we're going to have to use the second one, which says that f of x is equal to a times log of negative, right, x minus b plus k. We have to use that one where we have this negative here, remember the negative, because it's flipped about a vertical axis, right? There's a horizontal reflection in there. Okay, well, we know, right? We know b is 1, so I could go a little further. I could write this as a times log of minus x minus 1 plus k. And I still don't know a, and I still don't know k. But I can figure those out. Why? Because I just have to plug in 2 points that lie on the graph, right, of that log function. And I actually emphasize 2 points here, right? I know 0, 0, the origin lies on that graph, and this point right here, negative 3, 2. So I can use those 2 points, plug them into this equation, and I can solve for a and k. Okay, so I'm going to use those 2 points to find a and k. So let's do that. So I'll say use the point 0, 0 and the point negative 3, 2 to find A and K. And once I have A and K, I'm done, right? I have my entire function. Okay, so let's start with the 0, 0, 1. So if I plug in 0, 0, that means I have 0, right, for my f of x or my y. That's got to equal A times log of minus 0 minus 1 plus K. But first of all, 0 minus 1 is negative 1, right? And a negative 1 is a positive 1, so this is log of 1 plus K. But what's log of 1? That's always equal to 0, right? Just like if you have an exponential function and you raise it to the 0 power, you're going to get 1. If you take the log of 1, you're going to get back 0, right? Remember, the regular log graphs pass through 1, 0. So the input is 1, the output is 0. Right? So that's important to know. So this is just 0. So A times 0 is 0. So what does K equal in this case? K is equal to 0. Okay, great. So we don't have to worry about K. K is 0. Now I'm going to use the other point to find A. So I'm going to plug in 2, I guess, for Y. And then I want log of minus, and what is that? A negative 3 minus 1. And then plus K, but K is 0, right? So that's all I have right there. So this is equal to 2 is equal to A times log. Well, negative 3 minus 1 is negative 4, and then I have a negative out front, so that's going to be a positive 4. So then if I divide both sides by log of 4, that's going to be A, right? So A is equal to 2 divided by log of 4. So now I have my answer. So the equation of that graph, right, that function, that log function, that transform log function, it's going to be the following. It'll be f of x equals A, which we know is 2 over log of 4. And again, you could estimate that if you wanted to. I'm leaving it in exactly what it should be, but you could put that in a calculator and estimate it. And then the other piece is log. We had to still use that minus, right? And then it's x minus b, which we knew was 1. That came from the vertical asymptote. And then plus k, but k was 0. So that would be my answer. That's the equation of that graph. Right? That would be the function that represents that transformed log. Okay, here's another one. Okay, so here is my graph. And again, I want to come up with the equation, right, that gives the equation of that particular function, that log function there. It's a transform log function. So where do we start? Start with the vertical asymptote. So in this case, it looks like we have a vertical asymptote it's the line x equals negative 4, right? Because as we get closer and closer to that line, the graph is, in this case, blowing up. Okay. What does that mean? It means that the b, so therefore the b is equal to negative 4, right? So that gives us one of those parameters, right? We have those 3 parameters we need to figure out. We need to figure out a, b, and k. So we have b, we get that from the vertical asymptote. Okay, now which form of the transform log function do we use? Do we use the regular one or the one with the minus in front? Well, remember, to determine whether you use the one with the negative, it would have to be reflected about a vertical axis. In this case, it is not reflected about a vertical axis. It looks like it might be reflected about a horizontal axis. It looks like there might be a vertical reflection, but there definitely is not a horizontal reflection, right? Because normally Let me see if I can explain that. Normally, the log would start at negative infinity, come up, right? Go through like 1, 0, and then go off to infinity very, very slowly. If it's reflected vertically, then that means this piece, which is normally down here, would be up here, and then it's going to go towards negative infinity really, really slowly. So it looks like in this case it's reflected vertically, but not horizontally. So that means we can use that first form of the equation. So we want to use this form. F of x is equal to a, and then just log of x minus b plus k. So I don't have to use the one that has a negative x minus b inside the log, right? Because that would be if it was reflected horizontally. And it's not. It's reflected vertically. So because it's reflected vertically, what's going to happen? I'm going to get a negative for my a, right? But we will figure that out later. That means the whole function will be negative. But we want to use the first function for this particular example. Okay, now what? Well, we know b, right? So we could plug that in. Actually, let's just do that. So this is going to be x minus a negative 4, but that's the same as x plus 4, right? Plus k. And now I have to figure out a and k. And we're pretty sure a is going to be negative because it looks like it's flipped vertically, right? So how do I figure out a and k? Well, here's where I'm going to pick 2 points that are on the graph and then plug in those 2 points and then solve my systems of equations, my 2 equations for a and k. Well, it looks like the 2 easiest points to pick, and I kind of highlighted them here, is the graph is definitely passing through negative 3, 0. So I'll use that point, and it's definitely passing through this point, which is negative 1, negative 3. Okay, so let me plug in, I'll use the negative 3, 0 first. Give me some room here. So I have, my output is 0, right? A log, I'm going to plug in negative 3. We already know the b is 4, so I'll leave that as 4 plus k. But what's negative 3 plus 4? That's 1, right? So this is 0 is equal to a times log of 1 plus k. And earlier, remember we argued, and this is something you just have to know, you should know this really quickly, log of 1 is equal to 0. So this is telling us again that k is equal to 0. Okay, nice. So we just no additional term is added to the end, right? So k is 0. So now what I need to do is figure out a. So I'm going to use that other point, negative 1, negative 3, to figure out a. So if I plug that in, I have negative 3 is equal to a times log of negative 1 plus 4, and then plus k, but k is 0. Okay, so this is saying that negative 3 is equal to a times log of 3, right? Negative 1 plus 4 is positive 3. So then I can divide both sides by log of 3. Log of 3. And that will give me a. So what I'm finding here is that a is equal to negative 3 over log of 3. Good. That's good that we got negative, because remember, we knew that it was flipped vertically. So the a, the thing out front, must have been a negative number, and we got the negative by plugging in that value. All right, so that's it. So I'm done. I have everything I need now, right? So now I can figure out the exact equation for that function. It's going to be a, which we know is negative 3 over log of 3, and then times log of x, and then it was minus a negative 4, so that was plus 4, and then k was 0. So this is our equation. So this graph up here and the purple is the graph of that particular function. And that's what I put into Desmos to get that graph. So -3 over log of 3. Again, if you wanted to, you could get a value for that, but I'll just leave it. So that's exact times log of x plus 4. Okay, let's do one more. This one will be slightly more complicated because now I want to do one where the k doesn't come out to be 0. We actually have to do a little bit more work. Okay, so I'll do one more. Okay, so here is my graph of the transformed log function, and I want to come up with the actual equation, right? The function itself. So let's start again with looking at vertical asymptote, right? There's definitely a vertical asymptote. There has to be for any type of log function. And in this case, oops, I keep making that mistake. Let me go back. So vertical asymptote, in this case, it's x equals 2, right? Therefore, we know one thing, we know that b is equal to 2. So we have one of our 3 parameters. Right? Remember, we have to find a, b, and k. So we have b. B is 2. Is this graph, this log function, flipped about the vertical axis? No, this is like the standard. It's going in the correct direction, right? It's not even flipped vertically. It's just, it's a standard function. So we're going to use that form f of x equals a. And here's the thing. I'm going to tell you guys, just because it's going to come out easier, that when I did this, I used a log base 2. So I'd have to give you that. So I'm going to give you the fact that it's log base 2. So x minus b, which is 2, plus k. All right. So now that we know that general formula, if we can find a and k, then we're done. Then we have our actual equation. Well, how do I find a and k? I'm going to use 2 points that I know lie on the graph, so that I know that they satisfy that equation. So I can plug in those 2 points, and I can use that to find a and k. Well, what are the 2 points? I highlighted them here, right? One of them is, it's definitely going through the point 4, comma, and it looks like 2.5, or you could call this 5 halves. And then this point is 6, and it looks like it's 4.5, and the exact value is 9 halves, right? Or 4.5. Either way, I'll just keep it as fractions. So 4 comma 5 halves and 6 comma 9 halves. Those are the 2 points I know that the graph is passing through. Okay, so let's plug in those 2 points. So the reason why I use log base 2 is to make this come out a little nicer, right? Otherwise it could be complicated. So let me plug in the 5 halves, the 4 comma 5 halves first. So the output f of x is 5 halves, when the input x is 4. Okay, so I can simplify this a little bit, right? So I have 5 halves is equal to, this is going to be a times log base 2 of 2 plus k. And remember, what's log base 2 of 2? That's equal to 1, right? Log base b of b is always equal to 1. So this is equal to 1. So this first equation I have is 5 halves is equal to a plus k. Okay, great. Now, let me plug in the second point. So if I plug in 9 halves, that's going to equal a times log base 2 of, remember x is 6, right? 6 minus 2 plus k. Well, so this is 9 halves is equal to a times log base 2 of 4 plus k. Well, what's log base 2 of 4? You could either do that on your calculator, or if you think about it, let me do it on the side here. This is why I use log base 2, because it's just easier. I could also think about it like this, right? This is log base 2, and 4 I could write as 2 squared. So that exponent can come out front, and I have log base 2 of 2, but that's just 1, right? This is just 1. So 2 times 1 is equal to 2. So that's simply equal to 2. So this is saying that 9 halves is equal to 2a, 2 times a plus k, because we just found that this is really just 2. Okay, so if you think about this now, I have 2 equations by 2 unknowns, right? I have 2 equations, they're 2 linear equations in terms of a and k. So I need to solve those 2 equations by the 2 unknowns. To make sure I have enough room, let me do this on the next page. Actually, no, I can probably fit it here on the bottom. Let's see if I can fit it in the bottom. Okay, so I have 5 halves is equal to a plus k, and then the second equation is 9 halves is equal to 2a plus k. Okay, so what do you guys want to do? I guess we could use like elimination, right? Or substitution. It's kind of up to you. Let's say I want to eliminate, I guess let's do the k's first. So one of these, right now the coefficients are plus 1 and plus 1. If I can make one of them negative 1, then I can add the equations and get rid of the k. So let me multiply the first equation by negative 1. Remember, I have to do both sides. Because then this will become negative 5 halves is equal to negative a minus k. Right? And actually, I'm going to write it, I'm going to make more room over here. I'm going to write it this way. I'll put the variables on the left-hand side. So I have negative a minus k is equal to negative 5 halves. The first equation I can just leave, right? So that was 2a plus k is equal to 9 halves. Add the equations out. So this is where the elimination comes in, right? The k's are gone by design. What's negative a plus 2a? That's 1a, so there's just a. And then negative 5 halves plus 9 halves is 4 halves, which is 2. So I know that a is equal to 2. Okay, good. Now I need to go back and find k. So I can plug a back into any of the equations. I'll just use the first one. It looks a little easier. So I have 5 halves is equal to a. So that's 2 plus k. So if I subtract 2 now, well, what's 5 halves minus 2? Well, 2 is 4 halves, right? So this is telling me that k is equal to 5 halves minus 4 halves, which is 1 half. So now I have everything, right? I have b from the vertical asymptote, and then I use 2 points to find a and k. So now my actual equation is for that graph is going to be f of x equals a, that was 2. I had to tell you it was log base 2, so assume it's log base 2. And then of x minus b, but that was 2. And then plus k, but k we just found is 1 half. So that would be the equation. And that is exactly the equation I used to draw this graph. Okay, so it is a little bit of work to figure out what these equations are, and you have to be a little careful, but the steps are generally the same. The vertical asymptote will give you b, and then 2 points on the graph will give you a and k. The only thing you have to be careful with is if the graph is reflected about a vertical axis. So if it's a horizontal reflection, right, about a vertical axis, then you have to use the form where it's log of negative x minus b. If it's not reflected, it could be vertically reflected, that's fine. As long as it's not horizontally reflected, then you use the regular log of x minus b. All right, that's it. So that's it for section 4.5. And then there's one more section in chapter 4 on 4.6, and this is where we're going to use exponential and log functions to do some applications, right? Some applied problems. We're gonna do some modeling. Great, thanks.